All right, so welcome back everyone. Today in this video, we're going to be looking and starting transportation engineering. And we're going to be focusing specifically on geometric design. And so I have a few practice problems for you all. So let's dive right in. All right, so number one says, a highway has a horizontal curve with a radius of 700 and a side friction factor of 0.1. Calculate the super elevation rate required for a design speed of 60 miles per hour. All right, so how do we attack each problem? All right. Well, we first have to decide what we're given. So it looks like we are given the radius, which is 700. We're given the side friction factor, which is 0.1. And we're also given speed, which is 60 miles per hour. Okay. What are we trying to find? We're trying to find super elevation. Can we use a formula for this? Well, the first thing I would do is search super elevation in my FE handbook. So two things come up, and the first one shows what super elevation stands for. So it looks like it's a E, or it's represented by the variable E, and it's a percentage. All right. So in the handbook, it says the side friction factor based on super elevation. So for this particular problem, we need F, which is side friction factor. We need V, which is design speed. So it looks like we have a side friction factor already, which is 0.1. We have the speed, and then R, which is radius. So it looks like we have all the various variables we need to solve for this problem. So we're going to be using this formula that I highlighted to the right. I'll zoom in a little bit so you all are able to see it a bit better. Okay. So it's going to be 0.01 E plus F, which is what? 0.1, all right? It's a side friction factor, and that's equal to 60 squared over 15 times 700. All right, once I put that into my calculator, you should get your E. I'll just do this out. So what's 60 squared divided by 15 times 700? I get is equal to 0.34 minus 0.1 divide that by 0.01. And so I get my E is equal to 24.3%. Okay, so I get B for my answer. All right, let's move to the next one. All right. Number 2 says, calculate the tangent distance for a highway horizontal curve with a radius of 500 and a central angle of 25. All right. So let's go through our steps again. First step, so what are we given? We're given the radius, which is equal to 500 feet. Okay, and we're given a central angle. It's 25 degrees. Okay. What are we trying to find? Trying to find the tangent distance. They also let us know that this is a horizontal curve. So are there any formulas that we need for this? Well, I'm going to look in the horizontal curve section. And I'm going to look specifically for tangent distance. So I'm in here, and we can exit out of that. So I'm in here and I see that T stands for the tangent distance. So any formulas with T in it may help me. Right. So I'm here. So T is equal to R tan I divided by 2. Okay, so do I have I and do I have R? R we know is the radius, and I we can check to see what I is. So I is the intersection angle, which that and the central angle is the exact same thing. So we have everything we need to solve this problem. All right, so now it's just a matter of plugging and chugging. So T is equal to R times tan of I divided by 2. It's important that we have our units in degrees because our angle is in degrees. So T is equal to 500 tan. What's our I? 25 degrees divided by 2. Okay. And we want to plug that into our calculator. Once you plug it in, you should get 110.85 or B. All right. Let's go to number 3. Okay. So this one says, push that over just a little bit. Calculate the elevation of the PVC, point of vertical curvature, for a crest vertical curve with an initial grade of plus 3% and a final grade of negative 2%. The vertical curve is 400 feet. The elevation of PVT is 200 feet. All right, so we're going to start this one how we always start. So what are we given? we are given the grades. So grade 1 is equal to plus 3%. And grade 2 is equal to negative 2%. All right. The length of the curve is equal to 400 feet. And elevation of PVT is equal to 200. All right. So what are we trying to find? We're trying to find the elevation of PVC. All right. So to start, I kind of want to get a visual of what this would look like. So in the handbook, it does a great job of showing us that. All right. So this is for a vertical curve. It was in here somewhere. Okay, here we are. All right, so for vertical curves, and zoom in here. And so it's basically just saying that we have the elevation of PVT, which is here, which is 200 feet. It's 200 feet high. And then we also have the length of the curve, which is L, and that's 400 feet. And we also have the grades, right? So we have G, G2, G1. Back tangent. All right, so how do we get the elevation of this initial point of vertical curvature? And all right, so PVC. So we have, let's take a look here. We'll start with, I guess we have the tangent elevation, all right? So we're going to start with this formula to see how we can ultimately get this elevation of PVC. All right, so we have our talent. So we'll just start there. So the tangent elevation which is 200. So we'll say 200 is equal to the elevation of PVC plus G1, which in this case, we already know what G1 is. So G1 is our 3%. So it's 3% or 0.03 in decimal form. And then times X. Okay, so now we don't know what X is, right? Do not know what X is. So how do we solve for X? Well, we go to our formulas and we see that X is equal to negative G1 over 2A. That means we have to solve for A. I don't know what A is, so we have to do this, so that seems a little difficult. Let's see if we can use this other formula. Well, we have G1, we have the length, and we have G2. So it looks like we would want to use, trying to highlight it, but this second formula. So to get X, it's the second step. So I'll do it in a different color so we don't get confused. X sub M is equal to G1 L over G1 minus G2. All right. So that's equal to G1 is 3%, so 3.03 times 400 divided by G1, which is 0.03, minus a negative 0.02. Your signage is very important, so you keep everything. If it's a negative percentage, you leave it. You don't change your signage for this problem. So see what we get. You should get 240 for that. So basically what this is saying is the length of the curve is L. So the length along this curve is L. But what we're trying to do is get the horizontal distance from the PVT to the PVC. So that horizontal distance is important to help us solve this problem. All right. So going back. Now we can solve for PVC, our elevation for the PVC. So it's going to be 200 is equal to elevation at PVC plus 0.03 times the 240. And for your elevation at PVC, you should get 192.8 feet. So if you're thinking about this, it is a crest. So a crest just means that, you know, it's doing something like this. A sag is making like a happy face. That makes sense. Let's erase this. All right, so it's like a happy face. But yeah, basically it's just saying that the initial point is lower than the tangent. Hopefully that made sense. Basically, if we go a little bit deeper into this, I want you to know just the information that you need, but I feel like it's important to kind of, we'll say that this point and this point. Don't mind my drawing skills. Basically, similar to how they drew this, right? Our PV, the blue point is our PVT. And that elevation is at 200. And this point to the left is our PV, this green point is the PVC. And its elevation is the 192.8. So you can see that, you know, we go up the plus 3%. And then we come back down. Oh, this is up. And then we come down that negative 2% in grade. So a little crazy drawing, but hopefully that gives you an idea of what's happening on this problem. And I don't know if I even gave choices for this particular one, but your answer is going to be that 192. All right. This concludes, you know, the design. The geometric design. And in the next one, we'll be going through a pavement system design. So see you all in the next video.